I'm very happy to be in Istanbul. As you can see, this was something that was posted on the DevConnect Twitter account, so yeah, so my talk is about building a decentralized social network with set reconciliation, essentially. So that's kind of a lot. But I'm the founder of Kiwi News, and basically what we're doing is like a decentralized Reddit or decentralized Hacker News, basically. And I gave this talk already before at Protocolburg in Berlin. So it's a bit of a different motivation, but in general it's the same talk. So first of all, I think you know, many people when we're talking about you know, storage and so on in the blockchain space, then a simplified version of, you know, dealing with storage in social networks is just saying, like, you know, the NFT is the tweet, the NFT is the post, and that's how we're like dealing with storing these posts on social networks. And so I think, like, as far as I know, like, Lens started out with that basically, and I want to motivate why that may not be that good of an idea, and why we also might need to store this information off-chain, essentially. And so here you can see this is like from 2 years ago, I think. Basically the block height on the horizontal axis and the estimated gas costs on the vertical axis. And basically what you can see here is that the noise in the gas pricing was reduced, essentially. And so it means that there were, like, you just got a better price in terms of the storage that it cost you when you stored information on the network. But a problem is that the congestion here is priced really highly. So you can see on all of these red arrows, essentially, is when many people wanted to transact or store, gas costs rose up a lot, and basically what they are doing is they are destroying, with these very high prices, they are destroying the demands, essentially. And this is an issue, and we know that also from, like, more daily examples, right? Like, for example, when we're sitting in the car and we're like in congested traffic and so on, basically also costs surge because we have to wait for people to, you know, for the congestion to resolve and so on. And I mean, it's very similar here in this case. It's just we have like a fixed throughput, and this fixed throughput basically creates like higher costs if there's congestion. However, with these social networks, one of the things is that there is the Metcalde's law, which is this idea that the more people are on these social networks, the more utility they get, right? So, like in the case of the telephone network, if everyone has a telephone, it's actually really useful, whereas if just 2 people are connected, it's not useful at all. And so intuitively, it actually makes no sense to, you know, destroy the demand that the network is generating when you have a high amount of engagement. And here you can see, for example, Farcaster's daily active users. And at the point where, for example, Vitalik Buterin joined the network, there was like at that time an all-time high in the daily active users. And like, why would you want to pay more to be part of the network at that point? That's actually a good thing, right? That many people are engaging. And then there's another issue, actually, which is this. I mean, I've taken this liberally from I don't know, like the regular car traffic, but there's this problem of inducing demand, where if you decrease the cost of using a utility or commodity, actually what you are doing is you're inviting more people to use this utility. So in the case of like adding a new lane to a highway, well, suddenly maybe you've reduced the costs of you know, of standing in traffic every day for 30 minutes, so you actually made the thing suddenly more attractive, which means you're creating demand. And what this can mean is that while you thought, you know, adding another lane would fix the problem, actually now it doesn't fix the problem because you made it also more attractive. So there are even more traffic jams. And I think I mean, this is a kind of a prediction or a speculation because I think it hasn't happened yet, but I would assume that this also will happen for L2s, where we will just find like more use cases. Like, for example, this Ethereum attestation service, if you take the signed statement on-chain, I think this would be quite foolish at the moment on mainnet because it's just too expensive. But I think many people are experimenting with this on layer 2 because it's something you can do given the gas cost. And so we can see, I think you can argue that this is kind of like an induced demand use case. And Vitalik also wrote about this in his most recent post where he said that if we have this spectrum of chains that give you this kind of, you know, on one side they give you security, on the other side they give you scale. I kind of expanded this gradient a bit more, like because he basically started with like account key stores, high value financial transactions, ENS names, but like for Twitter we're really just shit posting, so it doesn't really matter if you're like getting a double sprint protection on that or whatever. So that's like all the way to the right, which means that these things have to scale a lot and they don't have, they're not demanding that much security. And so this is really my motivation why this protocol for set reconciliation is useful. And Farcaster, in case you don't know, is a decentralized Twitter, but they have introduced me to it with their white paper, and in the white paper there's like a section where they talk about this like set reconciliation protocol, and this is what we are going to learn in this. So if you're paying attention the next 20 minutes, you should conceptually like understand how they actually do that, and how you can build like a very simple peer-to-peer network on a conceptual basis. So the agenda for today then is really this, like it's what is set reconciliation good for? What are the technical challenges that we have to overcome? How does it work? And I will run through like two examples, one with bitmaps, a very like simple example, and then with Merkle trees. And then we will evaluate this very briefly. And yeah, so if you, like some people might say like set reconciliation, wait a minute, like why do we even need that? Like we have already working social media platforms, right? Like we have Mastodon that works, like why do we need anything else? And well, the reason is that Mastodon has like a very specific kind of way of moderating the peers in the network. And so here you can see, this is from Lefteris, someone in the Ethereum community, where I think he got into one of these Mastodon nodes, and then basically his account got suspended with the reason that they don't like capitalists on that node there, but that they would change their opinion for a bunch of Moneros and not making it public essentially. But that's like weird, right? That's not really the values I think that we embody. That like one person can just ban someone if they like to. And so I think to understand why this is happening, we have to like structurally look at these different networks and how they create their infrastructure. So like on the left, we essentially have Twitter, which, if you think about the user groups, then maybe we have like a Kiwi, a Cherry user group, you know, an Orange user group, and on Twitter they all live, you know, in this one circle essentially, and Elon is watching over everything and making sure that they all, I don't know, get along or whatever. And then on Mastodon, there is this, basically everyone can spin up their own node. And the node operator has certain administrative privileges, essentially, and so they can, for example, also make peering permission. So in this case, for example, we have the broccoli node isn't, for example, isn't connected to the Kiwi node, and that might be on purpose, actually, right? And then, for example, the broccoli node might have a different rule set, so it might say that fruits are not allowed in that instance or whatever. And there you can see why there can be these kind of arbitrary rules that are enforced by the network operators. And then on the most right side, basically, we have, I think, something more conceptually close to Farcaster and Kiwi news, where essentially each one of the peers in the network holds all of the data from all of the peers. And this is very similar to, for example, also how Ethereum works, where we all, when we are starting to run nodes, we all hold all of the same data. And what this allows is it bootstraps this like credible neutrality of the actual network. And so yeah, that's basically the summary. Is that the network maintains all data, and then that creates a peer-to-peer power structure where everyone is equal in the network, and there is no permission. There's no permission to peer with other nodes, and this creates this this credible neutrality. So this is really what set reconciliation is good for. And now I would like to dive more into the technical challenge of it, basically. So for this part of the presentation, if you want to follow along later in detail, you can go to this website. It's testday.com/kiwi/main, and there I've gone through, you know, how do you sync a Merkle tree and like the more mathematical kind of details. So you can also go through that by yourself later. And so yeah, technical challenge. So you have to think of it like this: like input and output on networks is a very fragile kind of component, and so like many errors happen in that space. And in this setup here, we basically have these different circles, and they represent network nodes. And we also have this legend of the different states. So I've chosen Pokemon. So we have like Charmander. Formerly this, by the way, the middle one was wrong. I finally fixed it. Shout out to Host Facts also for that. But anyways, I think the key concept here is really that that you can only evolve from Charmander into Charmeleon into Charizard, right? You cannot skip from Charmander into Charizard. And that's often a problem also when we're talking about like state transitions in networks, right? Like we cannot go from state 0 to state 2 if we're actually missing state 1, right? That's kind of the idea that I wanna make clear here. But in this case, on the right side, basically we have these different nodes, and they're communicating over the network. And we have one of the nodes which is offline, but they're all initially in this like Charmander state. And then basically what happens is that this peer A evolves and sends out this blue envelope to all of the other peers to basically give this instruction of evolving as well. And then what we can see is that essentially all of them end up getting the message, and they all end up evolving, except for the peer B, because peer B is actually offline, so it doesn't receive the message of evolving. And what we can then see in step 3 is that when peer A evolves again to the state 2 or Charizard essentially, the whole process basically repeats itself. These new types of messages, this time pink, are being sent. And here we can also see that peer B is actually online again. So it also receives this new pink message, right? However, while all of them end up being able to evolve, because they have been in the Charmeleon state, so they can transition into the Charizard state, right? Peer B cannot, because it's still stuck in the Charmander state, so it cannot evolve, and so it's sad. No, but this is really I think this is a core problem in networking, because basically you have these nodes that are offline, and they need to be able to catch up with the rest of the network, right? And you cannot guarantee continuous uptime for these nodes, and so this example is kind of an example. So yeah, exactly. Network connections are prone to errors. Offline peers must catch up to participate, and then the catch-up algorithm is essentially this set reconciliation algorithm that we're talking about, and that's the technical challenge essentially. So so basically, then the question is like, how does set reconciliation works? And I'm going to make two examples. The first example is with bitmaps, which is not very realistic, but I think it will help you to understand how it works, and then we'll go into Merkle trees after that. So first of all, we need another setup here, where basically in step 1 we have these different messages. So we're just going to have a finite set of messages A, B, C, D, E, and F. Then we have a hash function, and then basically we map the messages to the identities. So basically A would always equate 0 in the hash function, B 1, C 2, and so on. And then we have two nodes that are connected over a network, and they can store these messages, but they also, in a bitmap basically, they store the identity so that they can very quickly look into the bitmap and they can say, you know, 0 means I have A stored, or 3 means I have D stored, or 4 means I have E stored, and so on, right? Just faster access, I guess. And now we're really going to walk through like set reconciliation in very simple terms. So peer A essentially just sends their bitmap to peer B, and what peer B is doing is it basically goes through all of the messages that it has. It only has E and F, and it checks for which ones are not present on peer A. So in the second step, essentially, you can see that peer B then sends those messages that were not present in the bitmap of peer A to peer A. And so what peer A is doing is it just stores these messages in step 3, right? And actually at that point, peer A is already reconciled. I mean, we know that because we are looking at the system from like top down, but like the node might not know that, right? And then basically the process repeats, where essentially now peer B sends its bitmap with only you know, the two last bits marked as existent, and peer A actually goes through all of these entries. Basically, I mean, it would like basically look at the 0 identity, it would see that it has it. But it would also know that peer B doesn't have it, right? It goes through the 1 identity, sees that B, and so on. And then what this means is that peer A knows that A, B, C, and D are missing from peer B, basically. And that's why it's sending it over. And yeah, it's actually as simple as that. Like, now the nodes are reconciled, and basically what would happen now is that this process would frequently repeat, but I mean, since they are reconciled, they would just find that the two bitmaps are equal, essentially, so they wouldn't have to exchange messages. However, it's not that easy, because bitmaps don't work in the practical case. Like, first of all, there can be an infinite amount of messages that you can define by just like writing tweets or whatever. So our hash function would have to be probably like kcac256. And then if you think about kcac256 in bits, that's way too big to send over a network. And even if you use something like Bloom filters, for example, then they are non-deterministic, essentially, meaning they can have false positives. So you might have to like sync a couple of times actually to make it work. And then there's also a O of n complexity based on the set, because you have to go through each of the bitmaps slots every single time and compare them to your own. So there's not really like any kind of optimization in that data structure that helps you to validate that in a faster way. So therefore, we have to find a solution to make it a bit faster, make it deterministic potentially, and this is where Merkle trees essentially come in. And this is really the kind of algorithm that I think Farcaster and Kiwi News essentially uses conceptually. So in this case, the setup is similar. We also have these two nodes. We have peer A and peer B, and they store these different kind of messages. So we have a bit more messages here. We still have A, B, C, D, and E, and then we're generating the Merkle tree by by hashing the data and then hashing these two into the root node and so on. And then for P of E, we have essentially the same tree, but we also have G and H additionally. And so, I mean, as humans, for this small kind of tree, I think we can quite easily see we can easily compare the trees, right? So we can see that basically this like subtree of B1 is included in A, so that one here is here. And then we can also see that A12 and B23 is also the same. And I mean, we can also confirm that by looking at the data itself, right? E and F, and then A, B, C, and D. But how would we do that with computers that are just talking over a network, right? Like, how would we make this comparison? And so, in a way, it's similar to how I described this like problem statement, where essentially you have one node that is always broadcasting its root out to other peers. And in this case, this root message is like 0xUVW. And then for a node that receives the root, but ends up having a different root, here in this case P of E again, basically what we find is that the trees must be different, right? If the roots are different, root hashes are different, then the tree must also be different. And that's when we're starting to engage in like set reconciliation, and for all other cases we don't. So as you can see here, there's already one optimization, because if we have the same hash, we don't need to sync, right? We know already that we're good, basically. And so essentially this goes back to these trees where basically we have 0xUVW and 0xABC as root, and so they're different. And that's the first step of the set reconciliation. Actually, it's like here you can see I have showed this basically in this like in this other schematic that we also had for the bitmaps, and what we found is that there's a mismatch between the two roots on level 0 of the tree. And every time we find a mismatch, and this is like a kind of like a label that I'm giving in the algorithm itself, then what we have to do is we have to go one level down, and we have to compare the nodes on the level further down, essentially. So in this case, we have to compare the nodes on level 1. Who is still with me? Show of hands. Kind of. Yeah. I can tell you, it probably doesn't get more difficult than this. Actually, I think that's I think the level of complexity that we have. So because basically what is happening now is we're really just repeating that step over and over. We are comparing the nodes that we get from one of the nodes with our own tree, and then we're either labeling them as matching, mismatching, or as missing. So these are basically the rules. So in the level 1 case, okay, basically B sends over these two nodes in this one, and then basically what peer A will do is it will compare. First of all, it will look for this hash, because if you find the hash, right, it's pretty sure that we can also find, we can mark the whole thing as matching. So in fact, actually, we find the hash, right, 0xDEF. We can find the same hash on the A tree. I think I can also, I mean, I probably also showed this here, right? So basically this DEF, we were able to resolve it here. So that's done, it's matched. And then for the B12 node, we're also going to look it up by its hash first in the database, and it's 0xGHI. We cannot find it, and in the case that we don't find it, what we're actually doing is we're also looking in its position, because it might be that the hash is not representative, but it might be that there's like a mismatch in the tree itself, and that's what is happening actually. There is basically this A12, but it's essentially a mismatch. And so I think at this point it's important to introduce these kind of rules of the algorithm. Because essentially, if we find a node on the other peer and we can match it by hash, then we are sure that it's a match and it's basically the same underlying data on both nodes. If that doesn't work, we're going to look it up by path, and if we find a node at that path, well, I mean, we already know it's not the hash, right? Otherwise we would have found it. Then we label it a mismatch. If we cannot find it by either hash or path, so there's no node, we label it missing. And actually, if it happens to be missing, and it's also a leaf node in the tree, then we should insert it. And I will show you how that will work out. But maybe, first of all, since we had this match here between 0xDEF and 0xDEF here, basically what this means for the tree, going back to this idea of the optimization, is that we can already label the entire B tree as for B11 as matching, right? Because if we know that the hash here matches that on the other peer, then this node, this node, this node, this node, this node, and this node, they're also matching. So the only thing that we end up having to do is actually traverse into this part of the tree now, and that's kind of like where this algorithm is a bit more like optimized, especially when you're sending messages over a network. And so that's precisely what we're doing here. We're now traversing into the level 2, and we're looking at B23 and B24, and we're also, so that's the same thing. So basically, what we're ending up finding is that for 0x OPQ, we can find the same matching node, but on a different path. So this is A12 and this is B23. And then for B24, we're actually not finding the same hash, and in its place, we're also finding a leaf node. And so, but going back to this like 0x OPQ, essentially, I mean, this is also interesting. Because basically, even though the structure of the tree was a different one, right? The subtrees are ending up being matched. So here, this 0x OPQ is found here on the level 1, and here it's actually found on level 2. So, but this means we can also label these parts of the tree also as finished to sing, which means we actually only have to care about this part of the tree now, which means basically this is done, so now we only have to look at this. And I mean, as you see, we are coming almost to the end of the synchronization algorithm, because basically now POB is sending over G and H, so these are leaf nodes. And if we remind ourselves about the algorithm, we're looking them up by hash, we cannot find them. We're looking them up by path, we cannot find them. Which basically means we think they are missing, and there are also leaf nodes, which means we should insert them into our own tree. And this is precisely what is happening here. Basically, we are sending over the G and H leaf nodes. We are finding that they are missing, that they're leaf nodes, and we are inserting them into our own tree. And what is happening now is that the A tree essentially is updated with these new insertions, and through that, the root hash will update, and the root hash will update to the root hash of POB, basically. So we end up having synced these two trees, and that's it. That's basically the set reconciliation algorithm in like one round, like going through like in very fine-grained detail, I think. And yeah, so basically now the question is like, what have we gained from this, right? If we remember back to our original problem statement, we had this problem with the not being able to miss states and having to basically catch up on allowing nodes to be able to catch up on network states, and we also know that network connections are prone to errors. And then we have looked into like these different solutions. So we've looked into like bitmaps. I think I briefly discussed for like full of messages. Yeah, so Mac and we are working at Kiwi News. So Kiwi News is like a decentralized hacker news. It's in a way like conceptually similar to Farcaster, and that I worked with people from Farcaster also to build the same architecture and so on. And yeah, we are mostly like curating like crypto related content. And yeah, basically our node software is built on the concept that I just described. And yeah, that's it. Thanks for listening.
I think stack reconciliation algorithm is pretty much like async the limits tool. Async.
Yeah, it's async. Yeah.
Async the limits tool for synchronizing file directories between servers.
Yeah.
Are you asking me, is rsync built on the same set of reconciliation?
I think it's similar, not exactly.
I mean, there are a couple of, I think also like Mastodon, I'm pretty sure would also use a similar kind of protocol. I think generally, if you use like CRDTs, I think this is quite useful. Yeah.
But what about people spamming the network and sending a lot of messages and sending some nonsense hash? Say I have this thing, but actually there's no content.
Yeah. So I mean, there's a problem in that. For example, if you think back to like the example I gave with the two peers, what if one of the peers would be, you know, not trustworthy, had maybe malicious intent, and then maybe it would come up with like a tree that is, I don't know, just a, I guess like a invented tree or something, right? Like a
something that never get matched.
Yeah.
And make the whole network searching for those data, but it's not actually.
Yeah. In this case, I think you would have to detect, first of all, I think that you don't have any subset of messages in common, I guess, right? And or I guess you would run through the algorithm and you would just find that, for example, you happen to need to ingest this malicious node's entire tree. So like, for example, what we do is we have certain constraints on the messages. So we say you need to be an NFT holder. You need to, you know, your messages need to be formatted in a certain way. They need to be signed and so on and so forth. So that I guess there's still some potential for Byzantine fault behavior that you could exploit it, but it limits it down. And then I guess you could still, like, you could also like ban the NFT holder from you know, if the malicious node signed messages with a certain NFT, we could just ban the NFT from participating in the network or slash them or whatever. But at this moment, we don't have anything for that, like that guards that basically. Yes.
So is the Kiwi network an implementation of the Farcaster protocol, like the node?
I think it's not really, like, it's just inspired. Like I've talked to like Varun and other people in the community, and just like we just developed that in the last year or so, like in parallel. So to be honest, I mean, it might be that they're now doing like different stuff, but like when I was researching it, it was mostly this like set reconciliation based stuff.
But it doesn't sync with the Farcaster hubs.
No, it doesn't.
It's between Kiwi.
It uses the I guess the intersecting part where we use the same technologies like libp2p, and for example the libp2p gossip sub from ChainSafe. And yeah, I could imagine that you could even make that work, although it would become quite, I think, messy technically.
I want to follow up on the previous question. So it seems like this set configuration is constantly adding new lists, right? So I can have a hub that's constantly creating new lists, and the rest of the network has to pick it up. Right? So that can be a form of attack.
Yes.
I don't have to create an entirely new tree. It's constantly adding new lists that don't exist. And other hubs wouldn't have a way of differentiating whether that lead is true or not. Is that currently the case, for example, in Farcaster network?
I don't know. In the I'm pretty sure the Farcaster network has some kind of like security thing. Like for example, what you can do is like you could just put a constraint. So you say every regular user can only add like 10 messages a minute or something like this, right? Or they can only like so and so many posts every day. So I think you can narrow it down. I think what Farcast is also doing is they, for example, I think they create an order over their data. So they, for example, I think what they would conceptually like mandate is that the tweet needs to exist in order for you to like it. So you cannot just like something that doesn't exist yet or something like this. So there are like constraints that make it more difficult to do these things. But yeah, I mean, there's definitely, if you compare it to like Ethereum, right? There's no point in spamming the same transaction 10,000 times because you're just getting poor. Whereas I think with these kinds of networks where there's not the gas mechanism built into storing data, yeah, it needs to be a different thing that handles the spam basically. Yeah.
So a follow-up question. So like if you compare to, for example, like Secure Scuttlebutt or other like peer-to-peer networks you based directly on IPFS, for example, there is no global consensus. And I think in this case we do have a global consensus that's being replicated across different peers. So what's the kind of advantage being gained of maintaining a global consensus? Because I think in a lot of times in social networks you don't need global consensus because you only care about your friends.
No, it's true. I mean, I think for IPFS, by the way, I don't know about Scuttlebutt, but for IPFS, I guess you would like upload these different JSONs, and they would all get their different CIDs, and then you would have to index over them, right? So, like for example, in the case of creating a Twitter or a decentralized Hacker News, the order is important, right? So. For example, if you submit a link before me, then you should be the curator of that link and not I, or like, and stuff like that. So I think IPFS would be useful for example, storing the actual metadata. I think it's a bit more involved to then also create an index with it, but I think it's also possible, by the way. I think they, as far as I know, like TrueBlocks, this like ERC indexing project, for example, creates an index over all ERC tokens using IPFS. I don't know. To be honest, I think it's just shades of it's. I don't really know what are the benefits of doing one or the other thing. I think maybe one thing would be where we can have like control over what types of messages we would be adding to the network. So we can say, for example, you need to have an NFT to add one, or you need to, you cannot upvote twice and stuff like this. Although in the end, I mean, on IPFS, of course, you cannot avoid a person, for example, sending 2 upvoting messages, but you would anyways have to index at a later point, and then at the indexing stage, you would simply ignore the second upvote that is not according to rules. So to be honest, I think these systems, I think you can probably change them, use them quite interchangeably. Yeah.
Today I have 2 cents here.
Yeah.
I was mesmerized, like Sergey at Ceramic, and apparently we do set a reconciliation project right now. That's our future iteration of how we do synchronization between ceramic networks.
Ah, nice. Yeah.
Yeah, and you actually can think of that set reconciliation as a full replacement for IPFS's beat swap. Like, and it absolutely makes sense. Like, instead of using IPFS as a single component, single layer, you could use this thing.
Or even mix and match, I think. You could just use this as like the indexing part, like the Merkle tree, and then the actual nodes would be like CIDs, for example.
Yeah, the actual nodes could be CIDs, but then like what BitSwap does is it tries to, well, add a lot of magic on top and then transfer bytes. So if you add CIDs and Merkle and then send the bytes, it's effectively the same thing functionally.
Yeah, and what is nice, I mean, what would be nice, for example, in adding IPFS is that you can resolve the CIDs everywhere, right?
Mm-hmm.
Like whatever, you go to any kind of gateway and resolve them. And this you cannot do with Kiwi right now, because it's, yeah. Okay, thanks.